Okay, does anybody have any questions? Yeah.
Can we go over how to identify Miso stuff?
Yes, we'll do Miso. We'll do Miso compounds. What I'd like to do is talk about the difference between Enantiomers, Diastereomers, Miso, and then also how we determine R and S values for things like cyclohexanes or Fischer projections. So here's what I will do. So when we have a tetrahedron, we can write the tetrahedron in the tetrahedral form with two bonds in the plane of the screen and then the bold and the dashed. Now, R and S, to determine R and S, we have to put the fourth priority group on a dashed wedge. And we talked about different ways to do that, group switching, etc. There's another way to orient the molecule that's done quite often in sugar chemistry. And that is to orient this molecule so that the two bonds are towards you horizontally, and then two bonds are away from you vertically. So if I take my little tiny tetrahedron here and I orient it so that it's pointing, so that the horizontal positions are pointing towards you and the vertical ones are away. So here's the horizontal positions pointing towards you. Here's the vertical positions pointing away from you. Then it would look like this. And this is what's called a Fischer projection. Now, Fischer projection is often abbreviated with just bonds that look like that. Okay. And so it's understood that when you see a molecule like that, all the bonds aren't in the plane of the paper, that this is the equivalent of two horizontal bold wedges and two vertical dashed wedges. So the molecule oriented so that the two positions horizontally are towards you. And you can remember this by that is a bow tie. So these are sometimes called bow tie structures, just to get the horizontal in the right position. So this is called a Fischer projection. And when you're dealing with a Fischer projection, sometimes group switching is the best way to approach this, simply because it doesn't matter whether the four position, whichever dashed wedge the four position is on, you just have to put it on one of them. Okay. And if I just tilted this Fischer projection a little bit, it would look like this. So if I bring the bottom dashed wedge into the plane, I'm going to have two positions towards me and the one position back. And the reason that I would want to orient it this way is because if I took this molecule and I tilted it down, what am I looking at? What is that reminiscent of? Three bonds. The Newman projection. So if you're up here looking down on that, you would basically see the one carbon of the Newman projection, or the Newman structures. So Fischer projections are very similar to Newman's in the fact that we could grab, for instance, that position, and we could rotate those three bonds around. Or if you don't like that, you could grab the top dashed wedge and you could rotate the bottom three around. So the Fischer projection is very, very, very similar to a Newman projection, just it's a different perspective. Okay. And if you've ever, in your biology class, or if you go take biochemistry or genetics, you may see molecules that look like this. There'd be one more. So you might see a molecule that looks like that. That's a 1, 2, 3, 4, 5, 6. That's a 6-carbon sugar. That would be called a hexaldose. And so the sugar chemistry, people use Fischer projections all the time, because every one of these represents the bold wedge, and then the dashed wedge, and then more bold wedges. So you'll see those a lot in the Fischer, you'll see Fischer projections in the sugar chemistry, and that's what Fischer actually studied, was sugar chemistry, and developed this whole method for viewing them. So that's what a Fischer projection is. It's just a modified tetrahedron. Okay. So if we have a Fischer projection, what I want to do now is I want to deal with not one chiral center, but I want to deal with two. But before I deal with the two chiral centers, let's talk about what happens when you only have one chiral center. So here's what we know. We know that if we have two chiral centers, two chiral carbons, that those molecules, if you have a single chiral carbon in the molecule, you have the ability to have mirror image isomers. And those mirror image non-superimposable isomers are called enantiomers. Okay. So enantiomers are, the definition would be non-superimposable mirror image isomers. And that's kind of the introduction. That was in the introduction to chapter 6. Once you got beyond E and Z, it's, what is a chiral carbon? The chiral carbon has to have 4 different things attached to it so that it can exist in its handed chiral form, meaning that it is in 2 mirror images, bless you, that are not superimposable. Okay. When you have only one chiral center, every chiral center can be labeled as R or S. That's the configuration. So R and S are configurations. And the configuration is the exact 3-dimensional structure around a chiral carbon. So when we're determining R and S for a chiral carbon, what we're doing is we're determining the exact 3-dimensional way that those 4 groups are arranged around the chiral carbon. And they can either be R or they can be S, and R and S then are mirror images of each other. So when you have one chiral center, you only have one configuration because you only have one chiral center. Now, each enantiomer has a way of being characterized. And the way the enantiomers are characterized is based on their difference in physical property and their base in chemical property. So the physical property difference between enantiomers, there's only one. If I have a pair of enantiomers, they have the same melting point, they have the same boiling point, they have the same refractive index, they have the same, if I put them on a normal TLC plate, it would be one spot. They would have the same RF values. Enantiomers have exactly the same physical properties except one, and that's how they rotate plane polarized light. And so plane polarized light is the idea that you have electromagnetic radiation that goes in both directions. And this is a crappy drawing. But you have a wave in the X direction and a wave in the Y direction. You have two orthogonal waves, two perpendicular waves. And that's what electromagnetic radiation is, which is the light coming out of the fluorescent light bulbs. Those orientations are in all 360 degrees if they come out of a non-polarized source. Now, if they hit the surface, they actually do become polarized, but for the most part, the light that we see is unpolarized from an artificial source like a light bulb. What we do is we pass that light through a filter called a polarizing filter. If you have polarizing sunglasses, that's what those do. And basically, the polarizing filters kind of act like your picket fence, where only one orientation of the light is allowed through the polarizing filter. So you take all 360 degree orientations and you make one. And this is all physics. So when you have the one orientation of plane polarized light, if you pass it through the solution, a single chiral molecule will rotate that plane polarized light. And it'll either rotate it to be to the left, or it will rotate the plane polarized light to the right. The right is called dextrorotary, the left is called levorotary. So every enantiomer is either D or L. It either rotates the plane polarized light positively or negatively. And so when we're talking about enantiomers, one is the D enantiomer and one is the L enantiomer. Okay. How do you know that? The only way to find that out is by using an instrument called a polarimeter and see whether it rotates positive or negative. And we'll do that in a couple of experiments in lab. We'll do it with an Aleve tablet, naproxen sodium, and we'll also do it with a yeast. We'll do a reaction where the yeast enzymes are going to produce a product that is chiral as well. And I'll talk more about this next week in terms of looking at this. But the basics are we have a D and an L enantiomer. So up here with a single enantiomer, or with a single chiral center, one of these is D and one of them is L. And the only way I know is to use the polarimeter. So I have to isolate pure R or pure S, put it in the polarimeter and determine whether it's D or L. Some R molecules are D and some molecules, R molecules, are L. There's no correlation between D and L and R and S. It's up to the individual molecule. It's easy to find out whether it's D or L. You just put it in the polarimeter, see which way it rotates plane polarized light. Not so easy to find out R and S, because in order to determine R and S, you have to grow a perfect crystal of that material, meaning that you have to slowly crystallize it like we did in lab, only we got plates which were hardly pure and really perfect. But if you grow the crystal very, very, very small, or very, very slowly, you can get a perfect crystal. You pass an X-ray beam through it, and you can determine the exact positions of the atoms, including whether the chiral center is R or S. Every drug that is chiral has to undergo that test, because you have to certify to the FDA that you have the R or the S. And if you have a drug with more than one chiral center, you have to determine the chiral center R and S of each of the chiral centers. Then you also have to determine whether it's D or L. So for instance, if you have a headache and you take an Aleve tablet or a naproxen sodium tablet, that is the S. It has one chiral center it's the S form. And it turns out that it's the lever rotary form. And we'll do this in lab. The S form came about from X-ray crystallography, where they pass the beam through the perfect crystal. The L came because you put in the polarimeter, it rotates left. If you take that naproxen sodium tablet and it goes into your stomach with the HCl that's present, it then changes form. It's a deprotonated carboxylic acid that becomes a carboxylic acid. It then changes its rotation to D, but the chiral center didn't change. So for the naproxen sodium, the actual what you take, it's S configuration, L rotation. When it gets into your stomach, it's still S, but now it changes to D because it's a completely different compound. So the D and the L correspond to each of an enantiomer. But enantiomers can have one or more chiral centers. The key thing is that two enantiomers, a D and an L, are non-superimposable mirror images. And we'll talk more about that because that's going to, how do we know that two molecules are going to be enantiomers? We'll have to relate that with the R and S configurations.
Is it possible for both of the enantiomers to have the same rotation, like both BD and both BL?
Two enantiomers. No, the enantiomers means they have to be opposite. So one's D and one's L. And if it's a single chiral center, one's R and one's S. So that's because they have to be mirror images. And so the mirror image isomers rotate D and L. That's what we find. And that was done, just as a historical perspective, that was done by Pasteur, the guy who invented milk. Right? I used that joke when I first taught in Kansas, and then when I walked out the door to go back to my office, there was a whole group of smoking students, and they said, you know, he really didn't invent milk. And I said, I know, it was a joke. Well, we can't tell when you're joking or not. So I guess I have to announce this is a joke. But Pasteur did a lot of things, and the story is that he's in France, wine, a lot of wine in France. And what winemakers knew was that when they pulled the cork, they would have crystals on the inside of the cork. And there were three types of crystals. And he was the one that sketched them out, although there may be some controversy in that. But he basically pulled the crystals off the corks, put them on the table, looked at them under a magnifying glass or a microscope, and there were three forms. There was one form that was symmetrical. And there were two other forms that when he lined them up, they were mirror images of each other. And so what he did was the rumor is, or the story is, he painstakingly separated them with tweezers into three piles. And he knew about polarized light, and so he made solutions of them and passed plain polarized light through them. What he found was the symmetrical crystals, which were later found out to be Miso, they didn't rotate plain polarized light. The other crystals that were mirror images of each other did, one in one direction and the other in exactly the opposite direction. So Pasteur was the one that came up with the idea of using plain polarized light. He didn't invent plain polarized light, he just knew about it, and applying it to this idea of handedness of molecules. But it just so happens that some of the acids that are in wine crystallized in the cork in a form that lets you see that they were mirror images of each other. And when you have a 50-50 mixture of a D and an L, well, if one rotates this way and the other one rotates this way, they cancel each other out. That acid was what they called racemic acid. And so that's where the racemic mixture comes from. if it's a 50-50 mixture of the D and the L. So we'll go into more detail about that next week. But what we need to understand in order to determine whether two molecules are enantiomers or something else is that every chiral center is R and S, but the overall chiral molecule is either D or L. Okay? And that if they're mirror images, they're enantiomers. So that's the basics of that, and that's in the video in Wednesday's video, sort of the first part of it, which is an introduction to chiral molecules. So what we want to do here is this. I want to take, and I want two chiral centers. I'm going to put them in Fischer rotation or Fischer projections. I'm going to put the two low priority groups here, and then I'm going to put an OH here, a CH3 here. Maybe I'll put a CH3 here, and I'll put a chloride there. Okay. So again, this is the bold. These are the bold wedges. These are the dashed wedges. And so I'm going to start with a molecule that has two chiral centers. Now, I would like to write the enantiomer of those two chiral centers, of this molecule with two chiral centers. I want to write its mirror image. So if I do that, I'm going to simply have the mirror image, which I'm now going to write out with a full bold wedges. And so the mirror image of this is going to look like this. So if this is molecule A, this is molecule B. Okay. What's the relationship between these two? Since they're mirror image isomers and they are non-superimposable, I can't just move B and overlay it with A. You could say, well, what if I take B and I rotate it and I slide it over? Well, if I rotate it, these bold wedges, so in other words, if I rotate it 180 degrees, these bold wedges now become dashed wedges, so that when I slide it over here, I'm trying to overlay bold and dashed wedges, they're not going to match up. So these two are non-superimposable mirror image isomers, which means A and B are enantiomers. Okay, so A and B are enantiomers. Now, how many other structures can I draw from this? Well, we should start with a formula. It turns out that the number of isomers, and I'm going to say the maximum number of isomers possible is 2 to the n power, where n equals the number of chiral carbons. And that's just a mathematical thing. If each chiral center can be R or S, then the total number of combinations is 2 to the n power. So if you have one chiral center, you have R and S, 2. If you have two chiral centers in this case, how many possible combinations do we have? 4. So that means there's 4 possible molecules, 4 possible structures for this molecule, and we've written 2. So let's write the other 2. So how would I write the other 2? Well, let me, again, start with another Fischer projection. And let me do this. Let me use the top carbon's orientation from molecule A. And let's use the bottom orientation, not from A, but let's use the bottom carbon's orientation from B. So let's put the chlorine here, the CH3 here, and the H there. So now I've got the top carbon is the same as A, but the bottom carbon is the mirror image of the bottom carbon in A, but it's also the configuration for B. So this is another possible structure. So all I'm doing is putting together the four combinations. So what can I do to draw the last structure? Let's draw its mirror image. The molecule I just drew, let's draw its mirror image. So there's the mirror image. So C and D are non-superimposable mirror image isomers. So C and D are enantiomers. So when you have more than one chiral center, we look at the whole structure. And that whole structure can only have one mirror image. So for A, there's only B. For B, there's only A. For C, there's only D, and vice versa. So no matter how many chiral centers are in the molecule, there's only one non-superimposable mirror image isomer. There's only one enantiomer. Okay? So A and B and C and D are pairs of enantiomers. But what's the relationship between A and C? Or A and D? Or B and C and B and D? What's their relationship? Well, they're non-superimposable, number one. Number two, they're not mirror images. Right? Because A and C, the mirror image of A is B, not C. So these are non-superimposable, non-mirror image isomers. And what are they called? They are called diastereomers. A couple of letter changes, diastereomers. So non-superimposable, non-mirror image isomers are diastereomers. Okay. So in this case, A has one enantiomer and two diastereomers. And that's true for all the molecules. They have one mirror image, but then they have two other diastereomers to them. And what we need to do is we need to go back and put R and S's in here so we can see how enantiomers are related by R and S configurations and how diastereomers are related by R and S configurations. But we have two sets of stereochemistry terms here. Mirror images are enantiomers, non-mirror images are diastereomers. So is everybody kind of with me here? Okay, so let's go back and talk about enantiomers. So enantiomers have exactly the same physical properties except how they rotate plane polarized light, whether it's right or left. What about their chemical properties? Well, enantiomers will react with other non-chiral molecules the same. So if you are taking two different enantiomers and reacting them with a molecule that's not chiral, they'll react exactly the same. Okay. My example of that is when it starts to snow here, but sometimes at the end of the month, right? We'll go from 70 to snow in like 2 days. Welcome to Cleveland. You will get out, if you brought them, your winter gloves. And your winter gloves are chiral, just like your hands are chiral. You cannot superimpose your winter gloves. You cannot superimpose your shoes, right? Because there's a left and right shoe. And your feet are chiral. So we'll just deal with the hands. Hands are chiral, winter gloves are chiral. What happens when you try and fit your right hand into your left hand glove? It's a different fit than if you try and fit the right hand glove into the right hand. Right? When two things are handed, they react differently in the different handed forms. So it's perfect fit with the right hand glove, not so perfect fit with the left hand glove. Okay? Now, we go to lab. When you get the gloves out of the box in the lab, you pick out the right hand glove and the left hand glove, right? Right. There's a box of left-handed gloves and a box of right-handed gloves, right? No. And you've never even thought about that, probably. It's like, oh, all the gloves in the box fit both hands. Why? Because they actually have a mirror plane, or they actually have a plane of symmetry that cuts through the glove, so that if I took two of those gloves and I put them like this, I could actually superimpose them by going like this and bringing them over, because those gloves don't have a palm and a top, right? It's exactly the same. So the lab gloves are not chiral. So chiral molecules fit equally well into the non-chiral gloves. Get me a pair of chiral gloves, they don't fit the same. Same thing's true for reactions. If you have a chiral molecule, it will react with other chiral molecules differently, whether they are D or L. Okay, why is that an issue? Well, because if I'm going to make a chiral drug, and the reason I would make a chiral drug is because one enantiomer would be more effective than another. In the case of the Aleve tablets, the naproxen sodium, one of the chiral forms cures my headache faster. The other, actually, enantiomeric form, won't destroy my liver, but it has some liver toxicity issues. So when the manufacturer makes it, they have to get rid of the one enantiomer and keep the good one. And then they have to show that when it gets in my stomach, it doesn't form that other enantiomer that's going to have some liver toxicity issues. Okay. Worst case scenario was back in the 60s, the drug thalidomide was a sedative for pregnant women. They didn't know that the other enantiomer would cause horrible birth defects. And don't even look it up. There were kids without arms, and I mean, the other enantiomer was very bad in terms of causing birth defects. And the other one worked perfectly fine as a sedative. So one enantiomer in a chiral environment, well, what molecules in your body aren't chiral? And we'll get into this, but amino acids that make up proteins are chiral. The DNA has some chirality with it. Enzymes have made up of chiral molecules, so they have chirality as well. So when you get a drug in a chiral environment, it's going to react differently, the two forms. Even if even smell is chiral. So that I could take the same molecule that is in dillweed, well, the same molecule is in dillweed and in, and the other one will come to me, but there's two different oils, one dill, one caraway seeds. Those two molecules actually have this, or those two oils, like we make clove oil, those two oils have the same molecule in them, but different enantiomers. So the same molecule carvone is in those two, but one smells like dill, one smells like caraway. That means there must be chiral receptors in my nose to be able to differentiate between those two enantiomeric forms. And I'll show you an example next week of another chiral molecule. So enantiomers will react differently in a chiral environment. But physically, the only difference is plain polarized light. Now, diastereomers are two totally different molecules. They have different physical properties. They'll have different melting points, different boiling points, different refractive indices. Put them on a TLC plate and they'll separate into two spots. Shoot them into a GC, you get two peaks. Diastereomers are completely different molecules. And if they're completely different molecules in that form, they react differently. I'll show you an example next week of Sudafed. Right? Sudafed, there's Sudafed, pseudoephedrine, and ephedrine. Pseudoephedrine is what you have to go to the counter at the drugstore to buy if you have a stuffed up nose. You got to show them your driver's license, right? Because it's a precursor to methamphetamine. So the Methamphetamine Control Act of like 1990 says that you can only buy 3 grams of pseudoephedrine a day. I don't know why you need 3 grams a day. That still seems like a lot, but if you're into meth, then you have to buy tons of blister packs in order to make it. Or so I see on TV. Right? This is all Breaking Bad phenomenon. The whole idea of being the anti-hero if you're in a theater class, right? That he's the anti-hero. What he's doing isn't exactly it's ethically challenged, but yet he's viewed. Anyway, I digress. If pseudoephedrine is a diastereomer to ephedrine, and so they actually have different physical properties. If I shoot them into a GC as a forensic chemist, I can tell the difference. If I run them on a TLC plate, I see a difference. They have different melting points. So I'll show you the structures next week, but they are diastereomers. They're one form of a diastereomer, so that their enantiomeric forms would not. And even biologically, pseudoephedrine is used for stuffed up noses. Ephedrine is used to rev your metabolism so you lose weight, which is why it was banned years ago. There used to be like ephedrine-based stuff, and then people died of heart attacks because you can't rev up your metabolism to have your heart keep up. So then you die eventually. So they took that stuff off the market. But those two are just diastereomers, completely different physiological properties and different physical properties as well. So that's the difference between enantiomers and diastereomers. And ephedrine has 2 chiral centers as well, so it has 4 possibilities. And the 2 diastereomers are ephedrine and pseudoephedrine. So here are our 4 molecules. So what we need to do is put R and S to this so that we can tell the difference between diastereomers and enantiomers from the configuration standpoint. Now, let's take this chiral center first, the top chiral center. So hydrogen is number 4. I've got an O, a C, and another C. Well, the O becomes number 1. And then this CH3 versus this C with more than 3 H's attached to it. So here's a carbon with 3 hydrogens. What does this carbon have attached to it? It's got a C, a Cl, and an H. And so who wins of CH3 versus C with a CClH? This carbon then becomes number 2, and this carbon becomes number 3. Now, what I like to do is I like to pull the chiral center out of the molecule and just put the numbers down. 4, 1, 3, 2. So if that's the case, is 4 pointing away from me? Yes, it's on a dashed wedge. Going from 1 to 2 to 3, clockwise or counterclockwise? Counterclockwise. So the top chiral center here is S. Now, how about the top chiral center in B? What is it? R. What is it in C? S. What is it in D? R. How am I doing it that fast? Because I'm looking at whether they're the same or opposite, starting with my first one. So in B, we made the opposite configuration by drawing the mirror plane. And then we went back to its original configuration in C and then drew the mirror image in D. Okay. So it's not that I'm that good, although I am. Been doing this a long time. It's that I'm making comparisons. So all I need is the first one, I got the other 3. Okay. How about the bottom one? So how about the bottom one? I would pull that chiral carbon out, and what's number 4? The hydrogen. What's number 1? Hydrogen, carbon, chlorine, carbon. Chlorine's number 1. CH3 versus a C with more than CH3. That's going to be number 2. That's going to be number 3. So you can kind of see, as you do more of the RS problems, you're going to be able to go, oh, well, CH3 is always going to be number 3. Or might even be number 4. But a CH3 versus a carbon with anything else attached loses. So I got 1, 2, 3, 4. Is 4 pointing away from me? Yes. So I don't need to do anything. But I originally drew the molecule that way to save me time. So now going from 1 to 2 to 3 is counterclockwise, and so the bottom carbon is S. Okay. So now what are we going to do? Let's go back through the other ones. So in B, what's the bottom carbon? R, because it's opposite. In C, it's R because the chlorine is on the left, and in D it's S because that was the original orientation. So if I know one is R and I know it's a mirror image, then I know the other enantiomer chiral center is S, which is exactly our first relationship that we want to know. So when you have an S and you draw the mirror image of it, the mirror image is R. Now let's look at the molecules together. So SS, its enantiomer is RR. SR's enantiomer is RS. So what can we conclude about the configurations of enantiomers. Every chiral center in two enantiomers, every chiral carbon is the opposite. So when you have enantiomers, and it doesn't matter how many chiral centers you have, in order for you to be enantiomers, you need to have every single chiral carbon opposite. That's characteristic of enantiomers. Okay. Now what about B and C? They're diastereomers. So in B and C, what do I have? RR and SR. So what's characteristic about diastereomers? For diastereomers, you're going to have at least one carbon with the same configuration and at least one carbon opposite. That's what the diastereomers will be. And why do I say at least one? Because I want a rule that covers everything. So if I have 4 chiral centers, all I need is one to be the same and at least one to be different. So diastereomers, completely different molecules, same structural isomer, but with they're non-superposable, non-mirror image. At least one chiral center is the same, at least one chiral center is opposite. So when you have 2 chiral centers, you have 4 molecules. 2 pairs of enantiomers, and then the relationship, each molecule has 1 enantiomer and 2 diastereomers, is the way that it works. So that's how the enantiomers and diastereomers work. Now, does that kind of make sense? Here's what I'd like you to do for Monday. We can make this practice problems. Here's molecule A. What I'd like you to do with molecule A is, I would like you to do exactly the same thing. Write B and C and D. And then I would like you to write the R and S configurations for each of the 2 chiral centers. But there's a twist in this molecule, in this set. And that is that I want you to tell me what the relationship is between each molecule, whether they are non-superimposable or whether they are superimposable. Okay? Because the twist here is that you're going to have 2 molecules that are superimposable when you write the mirror image. So you're going to write the mirror image to A as B, then you're going to write the diastereomer of A as C, and then you're going to write the enantiomer of C as D. So these 2 will be enantiomers, and these 2 will be enantiomers, and all the other sets are going to be diastereomers. But what I want you to do is I want you to tell me if there's any molecules that are superimposable, And the answer is yes. There are going to be 2 of those molecules that are superimposable. And now we have superimposable molecules that are going to be superimposable, but they have chiral centers. And so those are going to become meso. So meso compounds are compounds that have chiral centers but are superimposable on, and you'll discover the other one. You'll discover the rest of that. Okay? So that's what I'd like you to do. Do it on separate paper. I'll ask at the beginning, we'll draw this out, and then we'll go from there. So right now the reading assignments are kind of like we're behind the reading assignments, which is okay, because I'll adjust those today and over the weekend. So on Monday, what we will do is talk about meso compounds, and then we will talk about doing RS as well as getting 2 molecules and telling me whether they're diastereomers, enantiomers, meso, etc. So we'll do that on Monday. Okay. And I will have your exams on Monday. It's been a long week.